Okay, hello. Do you see the desktop? Is everyone able to see it now? Okay. All right. Um, on the course website, I pointed out here that there's another homework assignment. It's not quite there yet. If you click on this, uh, oh, I didn't up. Yeah, it's not up there yet. So I hope that it'll be up there either later today or tomorrow. But I just wanted to I put the notice there now, just to remind you that there's going to be one more programming assignment. Okay. And it'll be due at very end, the last week of the semester. Okay, and we'll talk about it on Wednesday. So should be up there for sure by Wednesday, and we'll talk about it and it's about virtual memory. Okay, and then there's another reading assignment. Uh, the Today we're going to review paging and talk about translation Lookaside buffer. And this next reading assignment is how you throw the hard drive into the picture. Okay, something called beyond physical memory. Okay, so it's going to be the idea of how you have a hard drive that can extend the memory. So that'll be an important topic. Okay, so that'll be what we'll start on. Probably maybe get to it on Wednesday or next week. Okay, so there will be another homework assignment up there real soon, and there's another reading assignment. Okay, and today we're going to talk more about paging, kind of review what we did last week, and add on this idea of the translation look-aside buffer. Okay, so here's here's the picture we were playing with last week, and here's the description in words of what's going on over here. Okay, so remember, we want to map virtual memory spaces, and there's two of them here. There's a virtual memory space on the left and a virtual memory space on the right. We want to map them to the physical memory space. Okay, so we have two processes running in physical memory. And the key idea with paging is that you take virtual memory and chop it up into these things called pages that are all the same size. So virtual memory is chopped up into it's usually 4 kilobyte. It's chopped up into 4 kilobyte pages. And physical memory is also chopped up into 4 kilobyte pages. Okay, so over here, I should have add a little comment here. Oh, actually, I want to open this in the editor. Sorry, let me reopen that, but so I can make changes to it. Okay, so virtual memory is an array of virtual memory is an array of 4 kilobyte pages. You can make a point, I might add a comment up here that physical memory, this is an array of 4 kilobyte, but we call them page frames over here. Okay, so on this side, they're called page frames. Over here, they're called pages. Okay, the textbook tends to call them virtual pages, which is probably a good idea, because just when you say just page, it gets kind of ambiguous sometimes whether you mean a page in virtual memory or a page in physical memory. But most books use the word page to mean a page in virtual memory. And the pages in physical memory are always referred to as page frames. Okay, and like I say, our book tends to call the pages in virtual memory virtual pages, which is not a bad idea, but that's not a common term. Okay, so virtual pages and page frames are exactly the same size. So every virtual page fits in exactly one page frame. Okay, so physical memory is chopped up into page frames, and you allocate the page frames to the virtual memory spaces. And you use the page tables to keep track of who's been allocated to what. So like over here, this is page frame 0. That's page frame 0, and it's holding page 4 from this process. Okay, so now page 4 in this process, if we look in his page table entry over here says page 4 is in page frame 0. So the page table translates from page numbers, that's these numbers over here, to page frame numbers, that's these numbers over here. Page numbers are indexes into the virtual memory array of pages. Page frame numbers are indexes into the array of page frames, of physical page frames. Okay, so this is an array. These are the indices into the array. This is an array. These are the indices into the array. And the page table translates indices. You look up an index from over here as an index in here. So these indices are used as indices into this table. And then in the table, you look up the indexes into the page frames. Okay, it just takes a little bit of getting used to. It's actually not that complicated, but it sounds like a lot of words. And over here was the formulas being used. If a virtual address is made up of two parts. The page number, which would be telling you whether you're in this page, this page, this page, this page, or this page. So the page number picks this page. Then the lower order bits in a virtual address decide where you are in the page. So it's called the offset because the page number puts you at the top of the page. Okay, so the page number would put you right there or put you right there. And then these bits would say how far into the page you are. Okay, then physical address over here is similar. It's got a page frame number, which chooses the page frame, which actually puts you at the top of the page frame. And then the same kind of offset would put you somewhere inside the page frame. Okay, then the page table entries, which is the page table entry, which is one entry in here, holds a page frame number. It holds one of these. See, this part here is the page frame number. The page number is not in the page table because the page number is the index into the page table. The page number becomes the index into the page table. So it's not in the page table. Okay. Then the page frame number, the page table entry has these extra bits over here. Okay, so I just showed 3 of them in this picture. I showed 3 extra bits. In fact, there's usually about a dozen extra bits. Besides the page frame number, the page table entry's got a bunch of bits. They're not shown in this one, but it's shown over here. Yeah, every entry in the page table has a bunch of bits. So far, the one we've talked about has been the valid bit. Okay. We're going to talk about some other bits today, but the main bit we talked about was the valid bit. The valid bit is what determines whether one of these indices really is a page frame or not. For example, in this virtual memory space, the idea was the program's not a big program. It's a small program. It only needs 3 pages. So these 3 pages of virtual memory aren't in use by this program. If this program issued an address into one of those pages, the program should crash because that would be a mistake. The compiler decided the program only needed 3 pages. Okay, so these pages aren't in use. So down in his page table, okay, let's see, in his page table, see, these are pages 3, 4, and 5. Now, I put numbers in there because you have to remember that in a computer memory, you can never have anything empty. The empty here means I really should have wrote unused. Okay, so empty was really a kind of a bad word to put there. I mean that it's an unused page frame, a page. Okay, so but the page table, you can't really put unused inside of a page table. So there's a number, but you look over here and the valid bit is 0, means that that's not a valid number. That number is not pointing to a physical page. It's just saying that this page over here isn't in use. Okay, so these 3 bits here, 0, 0, 0, say that these 3 pages aren't in use. Okay, so that's an extra bit that needs to be in the page table entry because the page table itself, you can't just somehow put -1. I mean, maybe they could have used something like a negative number over here, but there's reasons why that wouldn't work. Yeah, these are actually unsigned numbers. To make them negative numbers, you'd have to actually add a signed bit, which would make the page numbers grow, which would just be a waste of space. So these are unsigned numbers. They're not 2's complement negative numbers. They're unsigned numbers. So if there's 10 bits in the page number, there only needs to be 10 bits in the page table over here. Okay, so there's no sense of wanting to use like a -1, and you can't use 0 here to mean unused because 0 is that page. Okay, 0 would represent that page there. So there's no number you could put in these slots that would somehow be a flag or a sentinel saying unused. So there needs to be a separate bit. That extra bit says whether that is a valid or not valid entry in the page table. Okay, right? So the page table is an array of page table entries. The page table is going to translate a virtual address into a physical address by using the page number of the virtual address as an index into the page table. The page table entry then, this is the index into the page table. You look up the page table entry, you get this number, you copy it into that field of the physical address, you copy this offset into here, and you've now got the physical address. Over here is the formula that does that. Okay. Okay. Here I've used like C notation. So page table is this array. Okay. You take the virtual address, you get the page number field out of it. You use the page number field of the virtual address as an index. So that's what the square brackets tell you. It's an index into the page table. Okay, so this guy's used as an index into the page table. But then you look up the valid bit in the page table. So you think of that as a field in the page table. So the page table entry's got this field and this field. Okay, so you look up the valid bit in that page table entry. If it's a 1, that's true. So then you can go ahead and translate the address. If that valid bit's a 0, so that's false, then you raise the interrupt. Okay, that's the memory management unit sends the interrupt back to the CPU saying that this was a failed translation. The program did something wrong. It issued an address in one of these empty pages, these unused pages, so the program should be shut down. Okay, so if the valid bit is a 1, you build the physical address by going back to the page table, using that index into the page table, looking up the page frame entry. Look up the I'm sorry. Yeah, I'm sorry. Look up the page frame entry in the page table. Okay, so take the virtual address, get the page number field out of it, use it as an entry into the page table, go to the appropriate page table entry, get the page frame number, okay, and concatenate it with the offset from the virtual address. So this offset is copied down here, and this is copied up here, okay? And they're concatenated together, and that's the physical address, okay? All right. It's a lot of little steps and a lot of little ideas, but if you keep thinking about it and reviewing these pictures, it's actually fairly straightforward, but it's a lot of details. So it's an exercise in remembering all the details so that you can then convince yourself that you can go through and reason through all these steps. Like I said in class at the end of class last week, the best thing you could do is make a list of all these words: page table entry, page number, page frame number, and be able to draw a picture using all those words. Make a list of all the words and try to be able, from the list of the words, be able to like write down this algorithm, write down these data structures, be able to draw the picture. If you can reproduce the pictures and the data structures from the words, then you pretty much understand them. So, page number, page frame number, page table entry, physical address, virtual address, use those words and then build these ideas from it. Okay. All right. Now, one thing that's interesting is that if the page number is the index into the page table. Okay. So the size of the page table is the number of pages in virtual memory. Every page in virtual memory has a page table entry. Okay. Now, if you do a little bit of arithmetic, you see that the page table is really big because on a modern computer, let's just use a semi-modern computer. Let's suppose the computer is 32 bits. Okay. So this is a 32-bit computer. Okay. Um, okay. So you have a 32-bit address space. So it's a 32-bit computer. Okay. And we said that pages are 4 kilobytes. Okay. Okay. Which is what? That is 12 bits. Okay. So if you think of an address is 1, 2, 3. Let's see. An address is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, there's 32 bits. Okay. The offset is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's where an address is divided between, this is going to be 20 bits, 20 bits of page frame number. Okay. So 20 bits of page frame number and 12 bits of offset. Okay. But what's 20 bits of page frame numbers? Okay. 20 bits of page frame numbers is 2 to the 20, which is 1 megabyte. So there's a megabyte's worth of page frames. There's that's not 1 million and 10 to the 6. That's 1 million, which is 2 to the 20th. Okay, and if you go back just real quick, Google will tell us. I forget exactly what 2 to the 20th is. It's not quite. It's 1,048,000. Yeah, so that's what 1 million. Yeah, that's what. Okay, which is that many. That's that many pages. It's a lot of pages. Okay, so virtual memory has that many pages, which is also how many page table entries there are, or how big. Whatever it is, also how big the page table is. So this is how big the page table is. The page table is 1 megabyte, but it's actually, that's not how big the page table really is. That's how many entries. Yeah. When I say how big the page table is how many entries the page table has. Okay. But that's so that's the number of entries in the page table. Actually, let's figure out how big the page table is. Okay. So that's how many entries are in the page table. But how big is an entry in the page table? Okay. An entry in the page table, well, it's got to hold the page frame number. The page table entry has to hold the page frame number and a number of some bits. The page frame number is 20 bits. Okay. The page frame number is 20 bits. I'm sorry. No, I'm sorry. The page number is 20 bits. The page frame number is much bigger than that. Okay, now let's go back and over here. In the physical memory, let's suppose your computer has 8 gigabytes of memory. Okay. Well, actually, no. Let's do it on a modern Pentium computer, the address space for physical memory is 48 bits. Okay, so remember that this is 32-bit virtual address space, but on a motherboard you'd buy today, you have a 48-bit. So this is 32-bit virtual address space. But on a modern motherboard, you have a 48-bit physical address space. Okay, so 32-bit virtual address space, 48-bit physical address space. Okay, so then, similar to what we did here, if you have a 48-bit address, if you have I'm not going to try. So suppose this is a 48-bit address. You'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bits for the offset. Okay, so this is the 12 bits of offset. So then this would be what? 36 bits of page frame page. Oh, yeah, I shouldn't have said frame here. That's 20 bits of page number. I was right. Yeah, that's 20 bits of page number. It's real easy to get page frames and pages mixed up. Okay, so that's 20 bits of page number. That's 20 bits to choose a page in virtual memory. Then this is 36 bits of page frame number. Okay, notice it's a good idea to draw these pictures. The more as we keep drawing these pictures and drawing these pictures, we kind of keep using the same ideas over and over again. And I'll give you some homework problems in a little while where for you to practice doing these kind of things, like drawing this picture like we're doing now and doing these calculations. There's some homework problems that I have that I'll give to you that make you practice computing different ranges of page frame numbers and virtual page numbers. Okay, so we have a 32-bit virtual address, 48-bit physical address. Okay, pages are 4 kilobytes, which is 12 bits, and that's pages and page frames. Pages and page frames are 4 kilobytes. Okay, pages here I really mean page in virtual memory, page frame, a page in physical memory, but they're the same size. Pages and page frames are 4 kilobytes. Okay, so so this is a virtual address. And down here is a physical address. Okay, we have 20 bits of page number and 12 bits of offset, and we have 36 bits of page frame number and 12 bits of offset. Okay, this 36 bits here, is what's stored in the pages. That's part of the page table entry. So the page table entry in this case is 36 bits of page frame number, and then a certain number of bits. Okay, and then extra bits. Okay, now what's a normal amount? Normally these things will get rounded out to a, let's see, 36 bits. What's the next closest multiple of 8? What's the next multiple? Let's see. Well, 40 or 48. You can do the 40 or 48. 40 is 5 bytes. This is 5 bytes. And 48 is 6 bytes. Okay, so you can imagine a page table entry being either 40 bits or 48 bits. Now, 40 bits doesn't leave very many bits over here, so probably this is what they would be using. So let's say 48 bits. Okay, so 36 bits of page frame and 12 extra bits. So that's 48 bits, which is 6 bytes. Okay, so a page table entry, a reasonable approximation of a page table entry in this case on a modern computer with a 32-bit address space and a 46-bit physical address space would be 36 bits for the page frame number and say 12 extra bits. And that's probably pretty close. Actually, I can show you a picture from this folder on the course website. There's a folder that has pictures of virtual memory. So there's this virtual memory folder. I downloaded it here. Oops, wrong. Here's a page table entry on a modern computer. Okay, there's how Windows this is from the book on Windows internals. They've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits of extra stuff. Okay, and that's about, was that what we guessed? Yeah, so that's exactly what we guessed. 12 extra bits. Okay. Remember, we got that by just saying there's how many bits have to be in the page frame number, and then there's going to be some extra bits, okay, in the page table entry, and let's just round up to a reasonable number of bytes. So rounding up to 5 bytes wouldn't be enough bits, so you go up to 6 bytes and you end up with 12 bits of page table entries, well, extra bits in the page table entry, okay? And they find a use for all of them. Actually, not, let's see. They used to have a couple of them as unused. Maybe they finally used all of them. Oh, no. Oh, actually, I'm sorry. The page table entry's got these 12 bits. There's the page frame number, but then they even have more stuff up here. So they actually are using 64 bits. They're using the whole 64-bit word for a page table entry. So the 12 was just a kind of a coincidence. They went all the way up to having 64 bits in the page table entry. So there's 12 bits, the page frame number, some reserved for future use. There's about 10 bits there reserved for future use. Then there's some bits that are going to be that are used by Windows that wouldn't be part of what our textbook covers. So there's more to this stuff than we cover just in the textbook. So there's some extra fields in the page table entry that we won't talk about. We'll talk about a lot of these bits here. We've talked about the page frame number. So you can see that the page table entry in their case is a full 64 bits. Okay. Now, we're supposing 6 bytes per page table entry, okay? But there are 1 million entries in the page table. So now we can say that the page table is 6 megabytes in size. That's the actual size. How much space does the page table take? It's at least 6 megabytes. In the case of Windows, it's actually more because in Windows, they don't use 6 bytes, they use 8 bytes for a page table entry. They go the full 64-bit, so they use 8 bytes. So in Windows, a page table entry is 8 bytes. So a page table is 8 megabytes, which is pretty big. Yeah. 8 megabytes for a page table is very big, and that's actually going to bring up the next topic in a minute. But the problem here is that a page table is way too big. You can't. Well, actually, there's 2 problems. We'll see. The page table is too big, and there's another issue with it also. Okay. So we've just done a calculation that gives us a sense of, let's see. Okay, so we just did a calculation to get a sense of the size of the page table. Okay, and we've just seen that page tables are pretty big, and it gets even worse because here we did a 32-bit virtual address space. If you can just do this kind of over again, you could suppose a 64-bit virtual address space. Now notice the virtual address space is much bigger than the physical address space. Okay, so you could do this calculation a second time, but with a 64-bit virtual address space. Pages and page frames are still 4 kilobytes. That doesn't change. Okay, now you have, was it 52 bits of page numbers. Okay, so now that means that you have 2 to the 52, which is, I'm not even going to try to write the number. You have 2 to the 52 number of entries in the page table, which is undoable. You can't even actually have page tables. When you get to this case, you actually don't really have page tables, because a page table that's 2 to the 52 rows is not possible. That's more memory than exists on planet Earth, I think. Okay, so you're going to have to change everything. The calculation we did here is a reasonable calculation, but for actually older computers, when computers had 32-bit virtual address spaces. So things were kind of reasonable back then. With 64-bit virtual address spaces, the whole notion of a page table kind of gets turned on its head. Okay, so you get here and you see that the number of entries in a page table is not doable. On the other hand, this part stays the same. The page table entries don't change. Okay, you still have 36 bits in a page frame. 36 bits of page frame address. So the page table entry is the same. It's still going to be, well, at least 36 bits of page frame number and 12 extra bits for stuff. Okay, but then you can't say anything about the size of the page table. Okay, if you have a 64-bit virtual address space, the virtual addresses are what change. The page table doesn't really, the page table entry doesn't change, but the size of the page table is undoable. Okay, all right. Now, let's look at a couple other bits. Let's go back to our picture here. Let's see if I can find it. Let's think of, there's a couple other bits that we can put over here that are easy to describe. Okay, any page of your program can hold one of two things. Actually, if you go back and when we talk about C programs, we talked about C programs as we talk about C programs as having code, yeah, and then there's data. So a C program has code and data. The code, remember, is code you wrote, code that the language wrote, and code that the operating system wrote. Okay, and the examples would that be, the easiest example would be you write the main method. The C language writes printf, and the operating system writes things like create process. Okay, and then The data, we also know, comes in kind of separate parts. Okay, so the data comes into the stack, the heap, and then there's the global area. Okay, the global. Okay, and actually the global is even divided into two parts itself between the initialized and the uninitialized part. So there's the initialized and the uninitialized. Okay, the interesting thing is you would probably put every one of these things in its own page or group of pages. Okay, so the code you wrote is going to be put into, depending on how big it is, it's going to be put into a page by itself or several pages, but it'll be kept separate from the pages that have the language library. And it'll be separate from the page that has the operating system library. So there will be a page for your code, a page for your code, a page for the library code, a page for the operating system code. Then there might be some pages for the stack and some pages for the heap and some pages for the global, the uninitialized, the initialized global variables. Okay. Not the interesting thing is these pages they're not, you shouldn't look at them as exactly the same kind of thing. For example, a code page doesn't need to be written to. All of these code pages should be only read from, okay? They should not be written to, okay? On the other hand, obviously these things need to be read from and written to, okay? So these pages, it'd be nice if these pages could be denoted differently than these. So for example, one of the things that malicious programs try to do is change the code in your program. One of the ways to attack a program is to modify the code in the program. Okay, so you would like to say to the computer somehow that none of these pages can ever be modified. So what you do is over here you can have bits that go along with entries in the page table. So you could have a bit over here that is a whoop, I grabbed the wrong pencil. Okay, so there's the valid bit. That's one we've been talking about. Now, just some other bits that you could have. You could have a read only bit, or a write bit, or an execute bit. So we'll talk about these three bits for now: read, write, and execute. Okay. If the read bit is set, that means you can read it. And if the read bit is 0, you're not allowed to read that page. Okay. So the page would only be for, you could write. Now, okay. So if that bit is 0, you can't read that page. Okay. Now, the write bit would be the opposite. If it's 0, you can't write to that page. If it's 1, you can write. I said this wrong. A 1 in this column here for read means you can read it. A 0 means you cannot read it. A 1 for the write column means you can write it. A 0 means you can't write it. And in the X stands for execute. In that column, a 0 means you're not allowed to execute that column, that page, and a 1 means you can execute it. Okay? So here's how we should think about this. We have a read, write, execute bit. Okay. What would 1, 1, 1 mean? Well, you can do anything you want with that page. Okay. What would 0, 0, 1 be? That would be what you want for a page that holds code. Okay. You can't read the code. What that means is the CPU can't issue a load instruction into the code. And that might be useful because hackers might want to know what kind of code you're running. So you make the code not readable, okay? So the code's not readable. A malicious program can't go in a page holding the code and try to figure out what code you're running. Obviously, the code shouldn't be writable. A malicious program can't go into a page that holds code and try to modify it. And the 1 bit means that the CPU can fetch instructions using the program counter from that page. So what this means is the X is 1 means that the program counter can point to that page and you can fetch instructions from it. The R and W bits mean that you cannot read or write those pages, so you can't, a malicious program can't do anything wrong with those pages. So this would be good for code pages, okay? Right. Now, on the other hand, 1, 1, 0, this would be good for, say, the stack, okay? Because you can read it and write it. Another common thing that programs do to attack your program, is they try to put code in the stack and then execute it. Okay. Okay. If you can't modify the person's code, like from here, and you want to attack a person's computer, what then you try to do is load code into their stack or their heap. So it's real common on a modern computer to mark the pages that are in the stack or the heap as read, write, not execute. That means that even if somebody copied code into the stack, if they tried to point the program counter at it, what happened is that if the program counter was fetching a page out of this page table, if you're fetching a page using the program counter, you check the execute bit, and if it's not 1, you would throw an error. What that means is, if you go back over here, this logic becomes a lot more complicated. Notice that this logic only checked the valid page. Okay, this logic only checked if the page was valid. But you can imagine this logic getting a lot more complicated, where you'd have another term here that says that, if the page is, so you might have something here that just says, and you have to check some other things. So first of all, the page has to be valid. If the page is not valid, it doesn't mean anything. Okay. Okay. If you're something like this, if you're issuing from the program counter, so the page is valid, and you're issuing from the program counter, and the page table virtual address dot page number dot. Now you look at the execute bit. Okay. Okay. So this would be checking that it's okay to fetch the page from the program counter's point of view. If it's a valid page and you're using the program counter and it's an execute page, go ahead. Otherwise, raise some kind of interrupt. Okay. So you have a whole bunch of if statements to check various things. Yeah. If you're accessing, notice that these extra conditions have to do with the kind of instruction the computer is doing. And they can get kind of complicated, but the computers do this. So for example, if here's another example. So here's an else if. Here's a more complicated one that's an else if one. Okay. So you're always going to start off by checking if the page table is valid. Okay. So if the page table is valid and it's a store instruction, so I'll just say, suppose somehow the CPU knows it's a store instruction and you have write access. Okay, so the write bit is set. Otherwise, you have to raise an exception. Okay. Okay. So the logic here isn't quite correct yet, but the idea is that you could have you would start making all kinds of tests. The CPU would have all kinds of logic that as it's accessing the memory management unit, it's not just looking at the valid bit anymore. It's using these bits, but it has to use these bits in combination with things like, what's the CPU doing? Is the CPU issuing something from the program counter? Is the CPU doing a store instruction? So if it's doing a store instruction, it should be able to do it needs to check the write bit. If it was doing a load instruction, you would want to be able to check that the write bit, or the read bit, I'm sorry. If the read bit's not set, you wouldn't be able to issue a load instruction, okay? So these are examples of bits that would be in a modern page table entry. You would have read, write, and execute bits. Okay, these aren't the only ones. They're actually, like you saw, Windows had 12 bits, but there's the valid bit and the read, write, execute bits. Those are read, write, execute are pretty common. Those sometimes they don't actually make it 3 separate bits. Sometimes they have ways of combining them. They may combine read, write into 1 bit. So either you can read and write, or you can't read and write. Okay, so sometimes they just lump those 2 together. So there's a single read write bit. So it wouldn't matter if you're doing a load or a store, you might check the single read write bit. Okay, so there's different ways to do it. There could be a separate bit for read and a separate bit for write, or there could be a read write bit. Then when a program is loaded into memory, and you fill up the page table, when a program is being put into memory and the page table is being written by the operating system with information from the compiler will put each page of the program in appropriate page frame, update the page table entry, and also put the right bits over here. If when it's loading the code part of your program, all the execute bits will be set to 1. When it's loading the data part of your program, all the execute bits will be set to 0. Okay? When it's loading the code part, the read-write bits will be set to 0, and the opposite with the data parts. Okay, so this is a good example of extra bits that can be in the page table, the read, write, execute bits. Okay, now
Excuse me?
there's another interesting bit you can put into a page table, something called the present bit.
Hey, Professor?
Okay, which was sometimes is called P. Okay, the present bit brings up a whole new idea. Okay, we've been talking about a paged memory system. So we're talking about a paged virtual memory system. There's something called a demand paged. It's a slight variation on a paged virtual memory system, something called a demand paged virtual memory system. Okay, here's an idea. Suppose my program has got a lot of code. Okay, I wrote a lot of code. I mean, some programs are tens of thousands of lines long, but a lot of that code never gets called. So for example, you write code that handles off-the-wall error conditions that you hope actually never happen, but happen very rarely. Okay, so you may have code that's very rarely called. Okay, why should code that's very rarely called be loaded into memory and never get called? Okay, so far we've been assuming that when a program is loaded into memory, all its pages go into physical memory. So in this case, like if a program had 3 pages, then the program uses up 3 page frames. If the program has 5 pages, if the compiler wrote the program to have 5 pages, 1, 2, 3, 4, 5 pages, then those 5 pages have to be allocated in physical memory. So what this is all pages are loaded at runtime. Okay, a demand page virtual memory system is a little bit, sometimes you can call it sometimes it's referred to as lazy loading. In a demand page memory system, you load pages are loaded only as they are needed. So for example, if your program had some code that was only called on a very weird error condition, that code would probably never get loaded into memory until it's actually called. Okay, now how will we do that? Okay, add to this picture the hard drive. So over here, I'm going to sneak it in here. Here's the hard drive, okay? The hard drive is where all the pages come from, okay? So this is the computer's hard drive. So that's the hard drive, okay? So you can think of the hard drive as a bunch of pages. So let me kind of chop it up into, let's see. Think of the hard drive as chopped up into pages. Okay. So the hard drive's a bunch of each one of these pages came from the hard drive. Okay. So maybe this page was over here, and this page was over here, and this page was over here. Okay. So the hard drive is a bunch of pages. They're actually not called pages on a hard drive. They're called sectors on a hard drive. But the hard drive is a bunch of pages, and sectors are the same size. So it's a bunch of these sectors. Okay. Your program sits in the hard drive as an EXE file. So your program sits as an EXE file in the hard drive where each sector of your EXE file is exactly one page of your program. And this is what the compiler's job is to do. The compiler's job is to write your program as an EXE file on the hard drive, where each sector of the hard drive mimics exactly one page of virtual memory. Okay, so whatever should be in this page here is exactly what's in this sector here. So when your programs run, this sector gets copied there, and then this sector would be copied there, and this sector would be copied there. So the compiler set those sectors up. Now, on the other hand, your program also has a stack and a heap. The stack and the heap are not part of your EXE file. So when your program is loaded, your EXE file mostly contains just the code. Okay, and it also includes the initialized data. The initialized data and the code are part of your EXE file. Okay, right? So when your program runs, the compilers made it so that your code is written to the hard drive as pages, and also the initialized data is all been initialized into one page. And then when you run your program, the operating system copies those pages into, well, it actually copies them into physical memory and sets up a page table. So like this one really is over here in the page table. And this one, which was this one, is really over here in physical memory. Okay, so the operating system loads your programs from the hard drive directly into physical memory. Okay, that's a paged virtual memory system. Now, what about demand paged? In a demand paged virtual memory system, what happens is when your program starts up, it starts up with an empty page table. And there's another bit. I have to add another bit to this column. Okay, so I'm going to add another bit. Oops, that's not what I want. Okay, so now there's going to be another bit over here. And it's what's called the present bit. Okay, the bit is denoted P for present. Okay, so there's the present bit. Okay, so this is the present bit. And initially, all these the page table is going to be empty. When your program loads, the page table will be empty. And the present bit will be set to 0 for everyone. Okay, so all these present bits will be set to 0. okay? So the page table is empty and all these present bits are set to 0, okay? Your program starts up. So your program issues a virtual address from this here. And that goes to this entry in the page table, okay? So suppose your code starts up here in this page over here. So that goes to this thing, and then that says that this thing's not present because it sees a 0 here. So then the operating system says that, oh, this page hasn't been loaded yet into physical memory, so now it's going to load it. So the page isn't loaded until it's asked for. At that point, the operating system says, okay, we'll go ahead and load this page. We'll see, where did we load it? We had it loaded at 4. Okay, so, but at that point, this thing says, okay, we'll put this guy at 4. Okay, and then we'll mark this thing as present. Okay, so when a program is loaded into memory, when a program is run, its page table essentially is empty. Okay, and all the present bits are set to 0. Then when the program starts running, the program gets to this program, the program counter starts in here, and this virtual address comes out here, and the page table says, but that's not present, okay? So in our logic over here, we have to start off with a case where it says if the page table entry is even present, okay? So all this would happen before you even, after you check whether the page is even present or not, okay? If the page is not present, then it has to be loaded into physical memory. When it's finished loading, then you can mark it as present, and then you can go ahead and look at, then you put the entry into the page table, you mark it as valid, okay, and then you set its read, write, execute bits appropriately, and then that page is going, okay. Then suppose something like the code accesses the stack, okay. The stack might be one of these pages down here, which at this point hasn't been allocated yet. So it'll have a 0 present bit, okay. So then when the operating system gets a virtual, when the CPU gets a virtual address that is marked as not present, that causes an error in the operating system, and the operating system then calls the loader. The loader's called when pages aren't present. Okay, so what's the difference? In the page virtual memory system, all the pages are loaded when the program starts up. Okay, so I can say at startup. That's what I mean, at startup. All pages are loaded at startup. Okay, now in demand paging, pages are loaded when they are needed, and that means when their present bit is 0. Okay, when their present bit is 0, that's when they have to be loaded. If you access a page and the present bit is 0, then the operating system has to come in and load it. Okay, all right. So that's called demand page virtual memory system, and Windows is like that. When you run a program in Windows, you would think that your EXE file gets copied into memory right away. And the truth is, it doesn't. It's actually kind of interesting. What happens is when you run a program, you get an empty page table, and then the program counter in the CPU is set to your main method, the starting point. And then the first thing that your computer does is it accesses the page table and finds out that main is not present. So your program starts up, and right away, the first page of your program has to be loaded. Then your program runs a little bit of code, and then it probably hits another page that's not present, and that needs to be loaded. So your program, we say, pages itself in. We use the phrase that the program pages itself in one page at a time. The beauty of this is that if there's a page of your code that's never going to get called because some error condition never comes up, you're not going to waste physical memory on something that's not going to be used. Okay, so the present bit is almost as important now as the valid bit. The present bit says that the memory location is in use, or is in The valid bit means that the memory location is in use. The present bit says it's actually been loaded. Okay, when your program is first brought up, I said the page table is empty, but the valid bits must be set. Okay, so when your program is loaded, the operating system knows how many pages should be valid, but they're initially not present, and then all the rest of these pages are invalid. Okay, so you got to make sure you understand the difference between being invalid and not present. Invalid, if you're invalid, the present bit doesn't matter. Invalid means that those pages are just not being used by your program. So invalid here means your program is not using that memory. Valid but not present means your program is that's legitimate memory for your program to use, but the present bit tells you where it's actually been loaded into physical memory or not. If you access a page that's valid and not present, there's nothing wrong with that, but your program has to pause while the operating system loads that page from the hard drive into physical memory, then can go ahead and access the memory, okay? So programs page fault themselves in. They page themselves in. Programs page themselves. This idea that a page is present, a page is valid but not present is sometimes called a page fault. Though page fault also means something else. This is one kind of page fault. In another chapter, we'll talk about another kind of page fault. So a page fault is the page is valid, but it's not in memory, so it's got to be brought into memory from the hard drive. And that means your program has to pause while that I/O is being done. Okay. So these extra bits are interesting because there's a lot of ideas in these extra bits. The valid bit is fundamental to virtual memory. You cannot have a virtual memory system without a valid bit. The other bits are all kind of optimizations, like the read, write, execute bit. They're really good for security purposes. They're not fundamental to virtual memory, but they're really useful from security purposes. The present bit is not fundamental to virtual paging, but the present bit makes you use memory more efficiently. You don't load pages if they're never going to get accessed. Well, you don't load a page until you absolutely know that it's really needed. Okay. Now, let's see if here's the valid bit. See, okay, here's Windows page table. There's the valid bit. See, they have a write bit. They don't have a read bit, but they have a write bit. Okay. Then they have bits that we don't really know what they mean, that we won't be talking about. Owner, write through, disable, cache. We'll talk about dirty and access later on. Now they don't have a present bit here. Okay. I'm not sure how they handle the present part in Windows. Okay. They don't Windows doesn't have the present bit in this page table, but they still have to have well, they have a P. Yeah, I don't know. Maybe they have a P here, which you think means present, because usually in these page tables, P means present. But then over here, you look up here, it says software field write. So I'm not sure what they mean. Yeah, I don't know what that means, but maybe maybe this one is the present bit. Okay. Right. So you can see they have a lot of bits. We'll be talking about different ones of these bits as we go along. But so far, the valid bit, that's the most fundamental one. A read-write bit. They don't have an execute bit here either. Okay. But I know that they have that ability to tell whether a page is executable or not. So it might be some of that might be somewhere up in here. Yeah. They might do some of it in some of these other bits. Okay. All right, so we've used these bits in the page table entry to extend paging from page virtual memory to demand page virtual memory, okay? All right, now let's talk about one last idea for today, the translation lookaside buffer. Let's introduce it, okay? There's two problems with this page. Okay, we said earlier that pages are huge. I forget where that file went to. we calculated that pages are huge, right? So you cannot have pages in the memory management unit. That's what it boils down to. They're too big to fit in the memory management unit. Okay. So let me draw another picture. Here's all right. Let's see. Here's a memory management unit. Okay. So the memory management unit, the first thing we saw that could be in it were the base and bounds registers. Then we saw that you could put pairs of base and bounds registers in it. What we've been talking about so far was the idea that in the memory management unit would be the page table. Okay, so we have the idea, we've been talking about the idea that you would put a page table inside the memory management unit. Okay, but the page tables are actually way too big. Okay, so we're going to put something else inside the memory management unit. We're not going to put the page tables in the memory management unit. The picture is going to look like this. The memory management unit, memory management is going to be here, and then we're going to have the hard drive down here. This is going to be the hard drive. Okay. The page tables are going to be down here. The page table is going to go inside. All the page tables are going to go inside the hard drive. So there's going to be a bunch of so all the page tables from different processes. Okay. So these are going to be the page tables. So this would be page table for process 1. Okay. And here's page table for process 2. And over here might be page table for process 3. The page tables are stored in, I'm sorry, not the hard, I'm sorry, I don't know why I said, the page tables are going to be stored in, they could be stored in the hard drive, but nobody does that. They're not going to be stored on the hard drive. Actually, that's one of the things they do in the more modern system. They do put them on the hard drive. We're going to put the page tables in memory. Okay, so the page tables are going to be in, the operating system part of physical. So the operating system is going to keep the page tables in its physical memory. Okay, so and then what's going to be in the memory management unit is going to be something called the translation lookaside buffer. So the memory management unit will hold this thing called the translation lookaside buffer. Okay. Okay. So we want to talk about what a translation lookaside buffer looks like. Now, in a page table, we looked at what page table entries look like. Now we need to talk about what one entry in the translation lookaside buffer is kind of an array also, like the page table. So it's this array. Okay. It's an array, but it's, instead of being, it's okay, it's not actually, it's not an array. Okay, this is an array, meaning that it's got these entries that are numbered. When you have an array, you have entries that are numbered. Okay, so you have entries that are numbered, which means you have an entry 0, followed by an entry 1. Okay, this is the translation lookaside buffer is not an array. This is not entry 0, entry 1. This is a hash table. Okay, it's actually there's various names for it. Okay, it's sometimes called a hash table. It's also called an associative array. Okay, it's got a bunch of fancy names: hash table, associative array. It's also called a map. It's also referred to as key value pairs. These are all different names for what this guy. It's a data structure that has various names: hash table, associative array, map, or key value pair. Okay, and what it is basically it's two columns. This is not an array. It's a table with two columns. Okay. The first column is page number. And the second column is page frame number. Okay. Now, the thing to do is it will compare the idea how these things work. Over here, that index is the page number. So you use page number. So if the page number is 1, that's your index into the page table. Over here, it's going to look something like this. I might have, say, okay. These are page numbers, 0, 1, 2, 3. And over here will be the appropriate page frame number. Like if I go to this picture we had a while ago, let me build the translation lookaside buffer for this guy. This is his page table. Let me write his translation lookaside buffer. Okay, his page table says page frame 0 is in page 0 is in page frame 1. So page 0 would be over here 1. Okay. Page 1 is in frame 3. So page 1 is in frame 3. Page 2 is in page 5. So over here, 5. And page 3 is in page 7. Okay. So this TLB here is equivalent to this page table here. Okay. And what it's saying is that, I mean, they say the same thing, but here you use the page number as an index into the page table. Here, what you do is you have to search the translation lookaside buffer for the page number. So here, suppose you wanted to look up page 3. So you go to index 3 and you get page 7. But you would just go straight to index 3 and get page 7. Here you'd have to search for page 3 and you'd find it at the first entry and you'd say, okay, page 7. On the other hand, if you're looking up page 2, over here with the page table, if you're looking up page 2, you use 2 as the index and you come up with 5. Okay. Here, if you're looking up page 2 in a translation lookaside buffer, you search the translation lookaside buffer for 2 in the page numbers. So 3 is not 2, 0 is not 2, 1 is not 2. Oh, there's the 2. Then you get the 5. You don't. Notice the 2 is not an index. These are not indices anymore. There is no row 0, row 1, row 2, row 3 in this data structure. It's not an array. It's a hash map, a hash table, key. You look up this. It's like a database. You can also think of this as a database where these are the keys and these are the values. So the page number is a key. You look up the page number in the table. And then when you find the page number in the first column, the page frame number is in the second column. Okay, so this is translation look-aside buffer idea. Why do we use this instead of page tables? Okay, most programs, remember we said there's 1 million entries in the page table. Most programs don't use only a few thousand of those. And the page table's huge. What this thing does, the translations look-aside buffer abstracts out of the page table just the useful information. So you can have a small abstraction of what is really needed out of the page table. Okay? Okay, so we ran out of time. I just noticed that we just ran out of time. Okay. So we're on Wednesday, we'll keep doing this idea of the translation look-aside buffer. Yeah, it's another tricky little thing to throw in there. The translation look-aside buffers are important in modern computers because the page tables are too big. So modern computers don't actually use page tables, they use the translation look-aside buffer. That's what's in the memory management unit. So we'll talk about that. They do use page tables, but the page tables are in memory while the CPU holds the memory management unit, holds the translation look-aside buffer. Okay, so we'll quit here and we'll pick up with the translation look-aside buffer on Wednesday, and we'll also on Wednesday go over what's going to be the new programming assignment. Okay, so I'll go ahead and quit now. If you have questions, send me an email and I'll upload all these notes and pictures up to the website. Okay, so I'm going to end the meeting now. Bye.